Okay, on to problem number 5 on pulse width modulation. So here we're just asked to calculate the duty cycles and period times, and I'll give a couple different methods to do that. Um, so we're going to calculate our T MR0 first, and that's going to be MR0 times PR plus 1 times T PCLK. That's our formula. That's always going to be the formula for MR1 and MR0. And we're just going to substitute, plug and chug here. So we're going to put in 1 million. We're going to put in 3 plus 1. And then we're going to have TPCLK as 1 divided by 50 times 10 to the 6th. And we plug and chug. That gives us 80 milliseconds as our outcome. So just plugging that into your calculator, running it through. We can then calculate MR time for MR1, which is our duty cycle, in the same way. So MR1, PR plus 1. Same equation, we're just substituting in our value for MR1 instead of MR0. So now we're going to have 200,000 times 3 plus 1 times 1 over 50 times 10 to the 6th. And that's going to give us 16 milliseconds. So what we're asked for here is the duty cycle and the period time. That is 80 ms. The duty cycle we're actually asked for in this problem, what I was expecting to get was the 16 divided by 80, so the fractional part of what that is. And so that should have been, that we are at a 20% duty cycle. So what portion of the period time is devoted to that? Though I think I did end up accepting 16 ms here as well because so many people gave that answer. It was not clear that I was asking for a percentage of the problem. But by technical definition, the duty cycle is the percentage. The duty period or the duty time would have been the 16 ms. So for the second one here, again, just plug and chug. So T MR0 is going to be our MR0 value, 500,000 times PR plus 1, 7 plus 1, times 1 over 50 times 10 to the 6th. And that's going to give us, again, 80 milliseconds. So let's get the duty cycle the other way now, which is if we have MR1 and MR0, we can see that the PR plus 1 and the TPCLK are going to be the same for both of these, right? So we can actually just determine the duty cycle by doing duty percent is equal to MR1 divided by MR0 is equal to 100,000 divided by 500,000, and that's going to give us 20%. And so we could also, calculate out the duty time then to sort of push this through, and T MR1 would be 0.2 or 20% times 80 ms, which is 16 ms. So we can also do that same exact thing, use that same calculation to find the duty time, and then we have 80 ms for our period time as well. Okay, so the last question here, explain what PMW1LER load enable register does and why it's necessary. So what it does is it transfers, MR0 and MR1 to the shadow registers. And so that's what it does. Why it's necessary is it does it at the same time. So it transfers them atomically or at the same time. Either way is fine. And maybe at the same time is a less technical definition of this. But really the important thing is that they are moving from the sort of staging area to the shadow registers where they're actually being used at the exact same instant of time. And so that way we're not dealing with any weird conditions where like we've transferred MR0 over, but we haven't transferred MR1 over yet, and an interrupt happens and that causes us to not transfer MR1 or something like that. It can cause crashes and the sort of ethical dilemmas that we run into where a piece of code that we write causes a radiation machine to malfunction or a pacemaker to malfunction or something like that. And so it's best to be able to do things atomically whenever we can, if at all possible. So that's it for that question.